Hey everyone, welcome to this explainer. Today, we're diving straight into Lecture 30 from Skip Uni. If you've ever found yourself scratching your head over recursion in C++, or you just want to deeply understand how recursion works in C++, well, you're in exactly the right place. We're going to completely demystify recursive functions in C++, really get into the weeds of the call stack in C++, and firmly map out the base case and recursive case. It's a total game changer for acing competitive exams and technical interviews, so let's get right into it.
Here's our roadmap for today. We'll start by defining recursion, look at the crucial base condition, map out the blueprint, trace the descent, hit the base case, and finally, look at popping and the final output.
All right, part 1, defining recursion. The core idea here is actually surprisingly straightforward. Recursion is simply a process where a function calls itself over and over again. Think of it like this. You've got a function, let's just call it f of x. When that executes, it literally contains a command inside it to call f of x minus 2. And then that new function calls itself again. It just keeps looping, calling itself repeatedly, right up until it hits a protective wall, which we call a termination condition or a base condition.
Moving on to part 2, the crucial base condition.
So, why do we need that protective wall? Well, function execution uses your computer's limited stack memory. Without a base condition, the function just calls itself infinitely. It never stops, eventually leading to a catastrophic crash known as a stack overflow. But when we add a base condition, we create this vital safeguard for safe termination. It basically tells the function exactly when to stop growing the stack.
Part 3, the blueprint.
Now, to really get this, we need to understand the exact sequence of operations. This specific execution problem is a classic. You'll see it all the time in product-based company interviews, so you definitely want to nail this down. Let's assume our base condition checks that our variable x is greater than 0. If we pass the number 5 into our function, making it f of 5, it's going to sequentially execute 3 exact steps. Step 1, print the value of x. Step 2, call the function again recursively, passing x minus 2. And step 3, print the value of x one more time.
Okay, part 4, tracing the descent.
Let's trace this step by step. We start by calling f of 5. Our safeguard checks, is 5 greater than 0? Yep, it is. So we enter the function, execute step 1, and print 5 to the screen. Then we hit step 2, which calls f of 5 minus 2, so f of 3. But wait, what about step 3? We still need to print x again. Because we just jumped up to evaluate a brand new function call, that final print statement is temporarily put on hold. It just sits there, paused, tucked away inside f of 5's isolated activation record in the stack memory.
Immediately, a brand new stack frame pops up on top for f of 3. The program checks the condition. Is 3 greater than 0? True again. So it executes step 1, prints 3, hits step 2, and calls f of 3 minus 2, which gives us f of 1. And once again, the control flow jumps. It has to pause its own third statement, printing 3, just waiting in its own frame for this new recursive call to finish up.
As we dive deeper, this really brilliantly illustrates the whole concept of local state. Notice how every single activation record has its own distinct local x value. The x in f of 5 is totally independent from the x in f of 1. They don't overwrite each other at all. So in our new f of 1 frame, 1 is greater than 0, it prints 1, then calls f of 1 minus 2, which is f of negative 1. And you guessed it, it pauses its final print command.
Part 5, hitting the base case.
All right, this is the defining moment right here. What exactly happens when f of negative 1 is called? Remember that protective wall we talked about earlier? Our base condition is checking if x is greater than 0, and well, negative 1 is definitely not greater than 0.
Since that condition evaluates to false, boom, our safeguard kicks in. The loop terminates instantly. The program doesn't even try to execute the print or recursive steps for f of negative 1. Instead, that f of negative 1 stack frame is instantly popped. It's destroyed, completely removed from memory. And this is exactly how we avoid that dreaded stack overflow. By hitting this false condition, the stack finally stops growing.
And finally, part 6, popping and final output.
So here's the really cool part. Understanding how the program handles all those paused statements we left behind. Control flows back down to the previous frame, which is f of 1. The program basically says, oh hey, I still have a pending third statement here. So it resumes that statement, which prints its local, completely independent value of x. It prints 1. Now that all its statements are done, the f of 1 frame is successfully popped right off the stack. And this unwinding process just continues. We drop back down to the f(3) frame, it resumes its own pending third statement, looks at its specific local value, prints 3, and then job done, the f(3) frame is popped from memory.
Finally, control drops all the way back to our very first activation record, f(5). It executes its final pending print statement, outputs its local value of 5, and pops f(5). And at this exact moment, every single frame has been destroyed and our call stack is completely empty. The program finished safely.
The result of this whole unwinding process is honestly pretty fascinating. Because we sequentially printed on the way down the stack, paused, and then printed again on the way back up, the final output sequence on the screen is 5, 3, 1, 1, 3, 5. It's this perfect mirrored sequence created entirely by how the stack functions.
Getting a grip on this hidden ascent back up the stack, and really understanding how local variables are isolated in their own separate activation records is the ultimate key to conquering product-based company interviews. If you can confidently draw it out this step-by-step trace and explain the popping process just like we did today, you are absolutely going to impress your interviewer.
Which leaves me with a final thought for you to chew on. Now that you've mastered this step-by-step blueprint, consider this. How would the call stack behave if a function called itself 3 separate times internally before it ever hit the base case? Just imagine the branches on that execution tree. Try mapping it out yourself using the exact same table structure we used today. Thanks for tuning into this explainer. Keep practicing those traces, and I'll catch you in the next one.